I'm Rob Jansen from the US Naval Research Laboratory. I'm going to present our paper, Co-opting Linux Processes for High-Performance Network Simulation. This paper was one of the two that won USENIX Best Paper Award this year. I'd like to give a shout out to my co-authors, Jim Newsome from Tor and Ryan Wails from Georgetown. Without them, this paper wouldn't exist and none of this would be possible. So thank them very much. The main takeaways: we designed a new hybrid network simulator emulator that directly executes applications and then co-ops them into a network simulation environment. This enables large-scale distributed system experiments. Our work is merged into the open source Shadow project, and it's synonymous with Shadow version 2. Our code name is Phantom in this paper. Our artifacts are available online. A brief summary of the results: we found that we're 2.3 times faster than Shadow version 1, 3.4 times faster than NS3, and 43 times faster than gRaIL, which is a similar approach based on NS3. And I'll get into why and how we do that in the following slides. I'll start with motivation and then go through the design and end with evaluation. So the requirements for distributed system experimentation are as follows. First, for any test network, we want it to be controllable so we can isolate important factors in our experiments, and we want them to be replicable so we can identically reproduce the results that we are achieving. Additionally, for large-scale distributed systems, we have additional requirements for accuracy. Large-scale systems, distributed systems in particular, are characterized by complex application logic. And so in order to accurately reproduce that, we want to directly execute the applications rather than an abstraction. And because of their scale, we need our approach to be scalable so we can decouple from real time and from the computational constraints of the host machine. So that's our goal. There are problems with traditional approaches where they don't achieve these goals. For simulation, an example of this approach is NS3. It's less realistic because it runs abstractions of applications rather than the real applications themselves. And as the applications are continuously developed over time, the abstractions can become outdated, and so it's hard to maintain those and can lead to invalid results. Another approach is emulation, which is the approach of Mininet. Emulation does run applications, so it's more realistic in that sense, but it's not as controllable. It's running on a Linux kernel, and so the results won't be identical because of the entropy on the machine. It's also not scalable. CPU overload on the host machine can result in time distortion that can introduce artifacts in the results. To verify this claim, we did an experiment where we ran a small peer-to-peer messaging workload in Phantom, our approach, and in Mininet. This graph shows on the x-axis as the number of hosts increases. After about 20 hosts in Mininet, the CPU overload caused the packet forwarding rate to be lower than expected. And so this demonstrates the CPU oversubscription that's happening during the emulation. So simulation and emulation don't work well, so there's been hybrid architectures that have been studied in research. This is a network simulation, but where the application code is directly executed. And the idea is to get the advantages of both simulation and emulation, and this provides the best opportunity for large-scale distributed systems. So there's been two different approaches with hybrid architectures. One is where the application code is run via plugin namespaces. So you literally just load the plugin, search for the main function inside of the code, and then call the function. This is the approach used by NS3 DCE mode, which is a research project that exists out there, and in Shadow version 1. The limitations of this approach are compatibility. You must build your program, your application as a plugin. Correctness, these approaches intercept library calls only, and so system calls made directly to the kernel will leak outside of the simulation and cause errors. And maintainability, this approach requires a custom loader and custom threading libraries, which can be hard to maintain. So this limits the set of applications that can run in this type of approach to those that satisfy all of these properties. And our approach is much more modular and supports a larger set of applications. And you can see the paper for more details on this. The other hybrid architecture is one where the code is run as a standard Linux process using something like fork and exec, and then ptrace, which is a Linux facility, to control the process. This is the approach used by gRaIL, which was published in Transactions on Networking in 2019. The problem with this approach is that it's slow. Ptrace is slow. It has overhead that is quadratic in the total number of processes that are loaded. And to intercept a syscall requires 4 context switches for every single syscall that's made. Transferring data between the processes and the simulator requires a syscall and a mode transition for every word of memory. So this overhead, we measured this overhead in gRaIL, which is built on NS3, to be 13 times that of NS3 alone, which demonstrates the overhead of the approach. So our research challenge is, can we design a tool with the performance benefits of the uniprocess plugin-based architecture and the improved modularity and isolation that you get from running real processes on Linux in the multi-process architecture? And so that is what we set out to achieve in this research. Next, I'll talk about the design and how we got there, and then end with some evaluation. Throughout the design discussion, I'm going to sprinkle in some results to help motivate why we made certain design choices, so be prepared for that. And in the upper right, I'm going to show sort of a schedule for the design components I'm going to discuss. I'll start with an overview. So we created a discrete event packet level network simulator. Again, it directly executes applications as standard Linux processes, and then intercepts all the system calls that they make, and then emulates them inside of the simulator process. So the simulation, we're simulating system call behavior and networking with functionalities such as file descriptors, event notification, networking, DNS, and routing is all simulated inside of the discrete event simulator, which runs in application layer without requiring any kernel changes. So the first design decision here is, how do we parallelize simulation workload? We have a simulation controller process that's running on a machine with several physical processors. And the simulation controller process runs multiple virtual hosts, each of them which runs some number of processes. And this represents the workload that the simulator wants to parallelize. So the question is, how many worker threads should we run inside of the simulator controller process to effectively parallelize this workload? And we tried some different approaches, one where we run 1 thread per virtual host, so that would be 7 in this example, or 1 thread per CPU, which would be 4 in this example. And these 2 graphs show that the 1 per host approach on the left was faster than the other approach, and on the right, also that it used more memory, which makes sense because this effectively means we're running more threads in Linux, and that has some amount of overhead, and so it uses more memory. But it's faster, so this sort of depends on your simulation environment or your host machine. If you don't have memory as a concern, then you can get away with that. But this is a configurable option that you can choose as you run these simulations. So we're going to choose 1 host per thread because it has better performance. Now, you'll note here that this means we're running 7 threads on 4 CPUs. And we want to avoid CPU oversubscription, as I just talked about is present in emulation approaches like Mininet. So to avoid that, we create a programming construct called a logical processor. And this will allow us to limit the number of threads that are concurrently active. We do that through an algorithm that is based on work stealing. The way it works is each logical processor starts a thread, and then it will run all events that are assigned to that thread in the current round, which is a simulated millisecond. Once that thread is finished running all of its events, it then sets that thread to waiting, and then we'll take the next thread that's waiting that hasn't been run yet in this round and run that one until its events are gone. And that continues until all of the workers' events are completed. And then the clock advances to the next round, and we repeat. Okay, so now we have a simulation controller process that will directly execute these applications. So how that works is as follows. The controller process is running in Linux on top of the kernel, and it will set some environment variables, including LD preload and an IPC environment variable, and then it will fork and exec the application process. Now, because we're setting LD preload to our shim library, this allows us to inject the shim into the application process as it's running. And we use this shim to then attach to an IPC channel that allows us to communicate with our controller process. So at the end of this execution sequence, we have an application running in Linux as a regular Linux process that can communicate with our controller process through an IPC channel. And then we want to intercept the system calls that the application is making. So to do that, first, I'll describe that the application is actually composed of multiple components. It has the application code in addition to a set of libraries that it's linked to. Now, because we injected our shim gets inserted as library 0 in the list of libraries. So whenever a function is called that does not exist in the application code, these libraries are searched in order for that function symbol. And the first library that has the function symbol, it will be called first. So we can use this approach to intercept library calls that are made normally that were made to the linked libraries, and we can intercept those to handle them inside of our shim. Now notice that this intercepts library calls, but not system calls. It's still possible for application code to directly make a system call using something other than libc, using an assembly language, for example. And so we need an approach to intercept those syscalls as well. And for this, we use seccomp, or secure computing. Seccomp is a Linux facility that allows you to create a sandbox for your application. It was designed in a security context to prevent applications that get hacked from making system calls that they weren't authorized to make. But we can use this in our approach to guarantee that any system calls that are not preloadable don't leak out to the kernel. We can trap all of those system calls and send them back into the shim so that we can handle them. So effectively, this application process is now running not really on top of the kernel because we're intercepting all of the kernel system calls and handling them inside of our code. So the controller is still running on the kernel and using it as it needs to. So we tested these two different methods for intercepting system calls, preload and seccomp, across different types of system calls, including a blocking system call, a non-blocking system call, and a system call that does read and write behavior. And we found that in all these cases, preloading is faster than no preloading. And the reason is quite simple, is because seccomp, in order to trap the system calls, seccomp requires not a full context switch to the kernel, but a mode transition to run the seccomp filter, and that does have a little bit of overhead. So we can avoid that. If we can, we would have a faster simulator. This is okay because in most cases, system call wrappers exist in libc, and so those will be able to intercept most of the functionality that the application is using. So next, once we have intercepted all of the library calls and system calls into the shim, we then emulate those functionalities by sending those over the IPC channel to the controller process, which can then emulate the Linux kernel behavior. So we emulate things like file descriptors, files, sockets, and pipes, event notification, pull, epull, select, networking, buffers and protocols, DNS, and routing. There's a small caveat here. We are allowed to emulate things inside of the shim directly. It's faster. It doesn't require IPC with the controller. So we can do this for hot path syscalls, in particular time-related syscalls, which are made often by applications. We can intercept those with the preloading approach and then just return immediately after returning the time, and this saves a significant amount of overhead. The other system calls will be sent through the IPC channel, which is a bit slower, and we want to send Syscall arguments and data over to the controller so that it can effectively handle the system calls. Okay, next is inter-process communication. How does this work? So we have an IPC channel between the process and the controller process and the app process. We're going to use shared memory as our IPC channel. And the reason is that we found this is the fastest approach when we tested it. We tested various approaches, including atomic flags, message queues, semaphores on shared memory, and domain sockets. We found shared memory and semaphores as the fastest for two processes that are running on the same core. So we're going to use that. And inside of shared memory, we're going to create a fixed size control block that we're going to place some state in, including semaphores, syscall registers, and the simulation time. And the other type of data that we need to transfer are buffers that are dynamically sized, such as those sent in the send call or the receive call, or reading and writing. Those buffers can exist in process memory, and they can be different sizes, and so we need to handle those. The way we do that is we actually remap the app's stack and heap directly into the simulation controller process. And when they're mapped into the controller process, we can read and write them directly without any IPC overhead and without any locks. And I'll get to that, how we do that in a minute. We tested this on buffers with different sizes, increasing here from 1K to 64K. And we found that our memory mapping approach, which is the middle orange bar, is the faster approach compared with a process VM facility that the Linux kernel provides. This process VM facility enables copying between processes without copying into application space, but we found memory mapping to work better, so we're using that. Now to control the running, to modulate the running state of the process, we use our semaphores. And the way this works is when the application process makes a system call, it will write the system call registers into shared memory, and then signal the controller semaphore to wake up the controller thread, and then it will wait on the app semaphore. The controller process will read the syscall registers, figure out which syscall it is, and what the arguments are. If it's a non-blocking system call, it can return immediately. Otherwise, it will leave the application idle and go back to the simulator and advance simulation time and return later when the result is ready. Once it does return, it will signal the application semaphore to wake up, and it will wait on the controller semaphore. So the properties that this gives us is that at any time, we only have one of the application process and the controller process that are active at any given time. And this ensures non-concurrent access to the app stack and heap memory, which means we don't need to lock accesses to that memory for efficiency. Finally, we use CPU pinning to pin a simulation controller process thread and all of its application processes that it's handling. We pin those to the same physical CPU core to take advantage of caching and to prevent cross-core overheads. And we experimented with both pinning and with real-time scheduling and found that the majority of the benefit consistently was due to pinning in our approach, so that's what we're using. All right, just a couple of slides left for the evaluation, and then I'll be done. First, we did a large peer-to-peer benchmark evaluation. These graphs show scales from 1,000 nodes up to 64,000 nodes, or processes. The left graph shows the total runtime of the simulation. We're comparing here ptrace, which is an optimized version of the gRaIL approach, to seccomp, which is our approach, to the uniprocess approach of Shadow version 1. The left graph shows the total runtime, and we find that we're faster and more scalable than the uniprocess plugin architecture across all scales. And on the right, we found that our memory mapping approach uses significantly less memory than the uniprocess plugin architecture. So with this peer-to-peer messaging benchmark, our approach was better in all cases. We were also curious how this works in a realistic network, so we tested it in a distributed Tor network. And here we find that performance in Phantom is comparable to Shadow, which is a state-of-the-art simulator for large Tor networks. As the network size increases, we approach the same performance as Shadow. So we think this is because Tor has a lot of computation in the application space, and so it ends up being, most of the overhead is due to the application layer itself. And then the right graph shows memory usage again, and again, we find that we're significantly less memory, we use significantly less memory than the uniprocess plugin architecture, from about 90 to 92% in the cases we tested. And I'll end again on the takeaways. This right graph shows Phantom compared to Shadow, NS3, and gRaIL, and that's how we came up with the numbers. This was in a peer-to-peer benchmark with 1,000 hosts. And everything else I already went over, so I'll stop here and be happy to take questions.